Welcome back to the deep dive. We're really thrilled you're joining us today because we have a piece of source material in front of us that
It
feels,
feels a bit like sci-fi, honestly.
yeah, exactly. It feels like a transmission from the very near, very weird future.
It really does.
Because, if you follow the space, everyone talks about the frontier of artificial intelligence. We hear a lot of noise about models writing better emails or generating images or parsing these giant data sets.
Right, the usual productivity stuff.
Exactly. But today's deep dive is exploring a single, profoundly revealing paper dated March 2, 2026, that documents something else entirely.
Something much bigger.
Yeah, and it was written by Donald Knuth, which, if you are anywhere near the world of computer science, that name commands immense respect.
Oh, absolutely. He's a legendary Stanford professor. People often call him the father of algorithm analysis.
Right, and the topic of his paper, it's a massive, undeniable leap in generative AI capabilities. We're talking about AI crossing the threshold into pure reasoning.
And it is hard to overstate how significant this particular author is. I mean, Don Knuth is a rigorous classical mathematician.
He is not a tech bro.
Not at all. He is entirely immune to Silicon Valley tech hype. So when he publishes a paper detailing an interaction with an AI, the entire computer science world pays very close attention.
Because it actually means something.
Exactly. We are not talking about a machine just, regurgitating its training data here. We are looking at a documented instance of an AI engaging in automatic deduction, creative problem solving, and literally the invention of novel mathematics.
Which is wild. And I want to set the hook for you right now by reading Knuth's exact opening words from this paper.
Let's hear it.
Quote, shock. Shock. I learned yesterday that an open problem I'd been working on for several weeks had just been solved by Claude Opus 4.6. It seems that I'll have to revise my opinions about generative AI one of these days, end quote.
That is quite the admission from a guy like Knuth.
It really is. Okay, let's unpack this. Because the context of how a machine managed to shock Don Knuth is arguably more fascinating than the math itself.
Yeah, the setup is incredible.
Right. So Knuth was writing a future volume of his famous book series, The Art of Computer Programming, and he was working on this puzzle involving directed Hamiltonian cycles.
Which we should probably contextualize the math for you here because the sheer difficulty of the problem is totally central to the breakthrough.
Definitely.
A directed Hamiltonian cycle is essentially the traveling salesperson problem pushed to its absolute theoretical limits.
Right.
You are dealing with a directed graph, which is a complex structure of nodes or vertices connected by one-way edges. And the goal of a Hamiltonian cycle is to traverse that graph, hitting every single vertex exactly once, and following the directional arrows to form a perfect closed loop.
Which is computationally heavy just on its own.
Oh, massively. But Knuth's specific problem added this whole other layer of complexity. He needed to find a complete decomposition of a specific complete directed graph.
Okay, what does that mean in plain English?
In simple terms, he had to extract not just one, but three entirely separate, edge-disjoint Hamiltonian cycles.
Wow.
Yeah, and they had to utilize every single available directed edge in the entire system without any overlap.
That sounds like a nightmare to nap out.
It is. Now, he actually solved this manually for the base case, which is a very small network where the parameter m equals 3.
Okay.
But, pure mathematics demands universal rules. You can't just solve one isolated case. Knuth was stuck trying to find a general construction that would apply to graphs of any size where m is greater than 2.
So it was just a completely open problem?
Completely open. He had been working on it for weeks.
Which is where the challenger in our story enters. Knuth has a friend named Filip Stappers who saw this open problem and decided to try an incredibly modern approach.
Yeah, he went straight to the AI.
He took the dense, formal mathematical wording of Knuth's problem and fed it into Claude Opus 4.6, which is a hybrid reasoning model. But looking at the source material, Filip didn't just, paste the text in and hit generate.
No. I orchestrated a masterclass in prompt engineering. He used extreme AI constraints.
Yeah.
Filip gave the model a strictly enforced framework for exactly how it was allowed to, quote-unquote, think.
He put guardrails on it.
Massive guardrails. He explicitly commanded the AI with this instruction, and I'll just quote the prompt here, after every explore xx.py run, immediately update this file, the plan.md file, before doing anything else, no exceptions. Do not start the next exploration until the previous one is documented here.
No exceptions. It reads almost like a manager speaking to a brilliant but maybe easily distracted employee.
That's exactly what it is.
Why is that specific rigid documentation rule so critical when you're dealing with a large language model?
It comes down to how these models inherently function at their core. An autoregressive language model only really thinks when it is actively generating tokens.
Right, it's predicting the next word.
Exactly. So if you ask it to solve a massive math problem and write the code immediately, it operates impulsively. It's just reacting to its own output token by token.
It's winging it.
It's totally winging it. But by forcing the AI to stop, open a separate markdown file, document its previous failure, outline its current hypothesis, and explicitly state its next logical step before writing any executable code.
It changes the whole dynamic.
It does. Filip essentially created an artificial prefrontal cortex for the AI. He forced an executive function bottleneck.
That is such a fascinating way to frame it.
Yeah, it slows the model down, forcing it to contextualize its entire search state and actually generate a coherent chain of thought.
And the incredible thing is that the paper actually lets us track that chain of thought step by step. We get this 31-step log of a machine attempting to invent a mathematical theorem.
It's like a diary of an AI thinking.
It really is. And looking at the first 14 explorations, Claude starts exactly how you would expect a computer to start.
With pure math.
With basic formulas, actually. It searches for simple, linear, and quadratic formulas, which just fail outright. Then it attempts pure brute force. It tries a depth-first search to simply calculate every single possible path through the graph.
Which, to be fair, is a brilliant strategy for a machine, assuming the search space is finite.
Right. Computers are great at calculating.
They are. But combinatorial explosion is the absolute enemy of brute force. The search space for just the absolute smallest network in this problem was 6 to the power of 27.
Which is... Wait, how big is that?
It is an astronomically huge number of permutations.
Yeah.
A depth-first search of that size would literally take until the heat death of the universe to resolve.
Oh, wow. Okay. And we see the model realize this in real time. Claude actually writes in its own internal plan.md notes, quote, "Too slow without good pruning."
It knows it's failing.
Yeah, it mathematically recognizes that its primary advantage, its pure calculation speed, is completely useless here. And here's where it gets really interesting, because the model doesn't just give up.
Right.
So how does an AI pivot when computation fails?
It shifts into high-level abstraction and pattern recognition. When it realizes it cannot simply calculate the graph, it decides to analyze the geometry of the graph instead.
Okay.
Claude successfully identifies the network mathematically as a Cayley digraph.
A Cayley digraph.
Yes. Now, for some context, a Cayley graph is a construct used in group theory to encode the abstract structure of a group into a geometric shape.
Got it. So it's looking at the shape of the data.
Exactly. By recognizing the graph as a Cayley digraph, Claude is leveraging deeply embedded structural symmetries. It begins finding repeating patterns within the data, and it decides to name them 2D and 3D serpentine patterns.
Just stop and think about that for a second. The AI is inventing and defining its own mathematical nomenclature.
It's creating its own language for the problem.
Yeah, it is building bespoke semantic tools to help it conceptualize a problem that it doesn't even fully understand yet.
It's an extraordinary display of emergent reasoning. And this structural analysis leads the model directly into explorations 15 through 26, which the paper highlights as a pivot to advanced heuristics.
Yeah, I noticed that.
In exploration 15, Claude introduces a technique it calls fiber decomposition.
I saw that term in the text. What exactly is the model attempting to do with a fiber decomposition?
So in graph theory, when a problem is too massively entangled to solve directly, you can sometimes project that complex graph down onto a much simpler base space.
Okay, like flattening it out.
Essentially, yes. You solve the routing problem on that simpler base graph, and then you lift those solutions back up through the fibers into the original highly complex graph. Claude is effectively trying to flatten the multidimensional complexity of Knuth's puzzle into manageable topological layers.
It's dismantling the problem, breaking it into chunks it can handle.
Exactly. And to navigate those layers by exploration 20, Claude decides to deploy an algorithm known as simulated annealing.
Simulated annealing. I love the name of that.
It's a fascinating heuristic.
Yeah.
It borrows a concept from metallurgy, where you heat a metal to a high temperature and slowly let it cool to alter its physical properties.
Oh, so that's where the annealing comes from.
Right. In algorithmic terms, you start the system at a high temperature, meaning the AI is programmed to purposefully accept worse solutions or make random, erratic jumps.
Why would it want worse solutions?
Because it prevents the model from getting stuck in a local minimum. That's a solution that looks good locally, but is actually a dead end. As the algorithm cools, it becomes more rigid, settling into the global optimum.
And the incredible thing is, the simulated annealing actually works for a specific, isolated case. It manages to find a valid decomposition for the M4 network.
It does. But an isolated case is not a theorem, it's just a localized approximation.
Right. Which brings us to arguably the most profound moment in this entire document, Exploration 25.
This is the turning point.
Claude hits an absolute cognitive wall. It reviews the data from the simulated annealing, looks at the strict constraints of the puzzle, and writes this in its plan file, quote, "Essay or simulated annealing can find solutions but cannot give a general construction. Need pure math."
The philosophical weight of that specific phrase, need pure math, generated by a neural network, is just staggering.
It gives me chills.
The artificial intelligence recognized the fundamental limitation of probabilistic guessing. It realized that no amount of computational trial and error, no matter how highly optimized that simulated annealing algorithm was, could ever prove a universal mathematical rule.
It needed logic.
Yes, it actively made the choice to switch its methodology from machine-like heuristic calculation to abstract deterministic deduction.
It's the exact moment the machine decides to act like a human mathematician. And that conscious paradigm shift is what sets up the final breakthrough in Explorations 27 through 31.
It really hits its stride here.
Claude starts testing highly complex geometric hypotheses. In Exploration 27, it tries an approach involving a single hyperplane and rotation. It seems incredibly promising, but it hits logical conflicts.
Right.
And then in Exploration 29, Claude writes a mathematical proof demonstrating that its own idea from Exploration 27 is structurally impossible. It literally ruthlessly kills its own darling.
That requires an immense capacity for logical objectivity. Think about it. It isn't just generating code anymore. It is actively falsifying its own hypotheses.
Yeah.
And because it cleared that conceptual dead end out of its working memory, it was able to look at the problem with completely fresh eyes. In Exploration 30, Claude looks all the way back to the data it generated using simulated annealing in Exploration 20.
It reviews its old notes.
It does. And it finds the signal in the noise. It has a true aha moment. What's fascinating here is that Claude notices a hidden algebraic pattern within the fiber decomposition.
Okay, what kind of pattern?
It realizes that the correct path at any given layer of the network doesn't depend on the entire structure. It depends on a single isolated coordinate.
Wow. Which radically simplifies the routing logic.
Totally.
And once it finds that lever, it pulls it. By Exploration 31, which, according to the timestamp in the paper, was just 1 single hour into this entire session. Just 1 hour. Claude writes a Python program that perfectly solves the general decomposition problem for all odd numbers. It works universally for 3, 5, 7, 9, 11, extending to infinity. The model outputs this celebratory note. All 3 cycles are Hamiltonian, all arcs are used, perfect decomposition.
So a machine solved an open problem in graph theory that had stumped a Stanford legend, and it did it in the time it takes most of us to eat lunch.
Yeah, unbelievable. But Knuth, being the rigorous academic he is, did not simply look at a clean Python output and declare the problem solved.
Definitely not.
No, he had to actually verify what the machine had done. Knuth took the AI's Python code and meticulously converted it into C, which is a much lower-level programming language, to rigorously analyze its memory allocation and operational logic. He basically spent time reverse engineering the machine's discovery to mathematically prove why the Python code worked.
And the scale of what Knuth uncovered during that verification phase is mind-boggling.
Tell me about it.
When analyzing the logic Claude used, Knuth found that for the original simplest base case of M3, there were 11,502 possible ways to form Hamiltonian cycles.
Okay.
But out of that massive cluster of permutations, Knuth proved that there are exactly 760 specific structural generalizations that will universally hold true for all odd numbers.
So 760 paths out of over 11,000.
Exactly. The AI had successfully navigated through all that noise to find one of those 760 universal paths. Knuth was actually so taken by this that he officially dubbed these 760 solutions Claude-like decompositions in the formal literature.
The AI literally got a mathematical structure named after it. That is amazing.
It's historic.
But there is a detail Knuth includes in the paper that adds a lot of character to this whole discovery.
Oh, I know what you're going to say.
Yeah, even though Claude solved the problem flawlessly, Knuth points out that the specific path the AI took wasn't necessarily the nicest or most elegant solution among those 760 possibilities. It just found one that was logically sound.
Which really speaks to the true nature of machine intelligence. Human mathematicians often search for elegance, right? They want symmetry and aesthetic beauty in a proof.
They want the math to be pretty.
Exactly. But the model simply searched for validity. It bulldozed a path through the topological woods. It didn't bother planting flowers along the side of the highway.
That is a great analogy. Now, as seamless and miraculous as this 1-hour breakthrough sounds, we have to look at the reality of this interaction.
Yes, we do.
If you are sitting there listening and thinking Philip just typed a prompt, grabbed a coffee, and came back to a Nobel-worthy math theorem, you are missing half the story. The source material reveals an immense amount of friction in this process.
We absolutely cannot romanticize the user interface of frontier AI. Philip was actively wrestling with this model the entire time.
It wasn't smooth sailing.
Not at all. Claude didn't march linearly from exploration 1 to 31. The system crashed repeatedly. It would throw random, completely inexplicable syntax errors.
Oh, no.
At certain points, the context window would seemingly overflow, and the model would completely hallucinate.
Yeah.
It was losing track of its own variable states and literally forgetting the search results it had just generated 2 steps prior.
And this is where Philip's strictplan.md rule saved the entire project. Left to its own devices, the AI would have abandoned the meticulous documentation completely.
It would have spun out.
Philip had to play the role of a hyper-vigilant manager. After every few iterations, he had to manually interject and force the model to pause, reread its instructions, and update the markdown file.
And if we connect this to the bigger picture of using AI for deep reasoning, it shows that the attention mechanisms in these neural networks are still quite fragile over long, recursive tasks.
Yeah, they lose focus.
The reasoning engine itself is profoundly capable, but its inherent executive function degrades quickly. It requires a human in the loop to essentially hold its focus and enforce structural discipline.
Which perfectly transitions us to the lingering mystery of Knuth's paper. We spent this whole time discussing how Claude brilliantly found the universal rule for all odd numbers.
Right.
What about the even numbers?
Ah, yes. That is where the machine finally met its match. It remains an entirely unsolved mystery.
Really?
Yeah. Now, to be fair to the AI, the simplest even number network, the M2 case, was mathematically proven to be structurally impossible by human mathematicians Ober and Schneider way back in 1982.
Okay, so M2 is off the table.
Exactly. But the open question was whether a general rule existed for the larger even numbers, like 4, 6, 8, and beyond.
And the text notes that Claude did find localized solutions for specific even networks, right? It solved the M4, M6, and M8 cases individually.
It did, but when Philip prompted it to find the universal rule connecting them, it just failed.
It couldn't do it.
And this is where we see that cognitive degradation we just talked about manifest in real time. According to Philip's notes, after the triumph of the odd numbers, he asked Claude to keep pushing on the even numbers. But the system seemingly hit a cognitive wall.
It was exhausted.
It lost its structural grasp on the problem. It began writing bizarre, broken exploration programs. It couldn't even execute its own Python code correctly anymore.
Man.
Eventually, the degradation of its reasoning capabilities became so severe that Philip had to shut the session down and completely abandon the search for the even numbers.
It is almost biological in a way, like watching a brilliant mind exhaust its mental stamina and just collapse.
It really is.
So, looking at the entire scope of this paper, we are examining a truly historic moment in computer science. In the span of a single hour, guided by a strictly enforced framework, an AI navigated 31 complex logical explorations. It recognized the limitations of its own computational brute force, actively pivoted to abstract pure math, created its own mathematical terminology, disproved its own faulty hypotheses, and ultimately solved a multi-week open problem that had stumped one of the greatest algorithm analysts alive.
That's completely unprecedented run.
And Donald Knuth, the ultimate skeptic, concluded his paper by stating that the late Claude Shannon, the brilliant father of information theory whom the AI is named after, would be incredibly proud.
So what does this all mean for you? The immediate actionable takeaway here is methodological. This paper proves that we have crossed into an era where AI can function as a deeply capable, albeit messy, thought partner.
Yeah.
but the quality of the output is entirely dependent on the structural constraints that you provide.
The guardrails.
Exactly. The next time you are using an LLM to tackle a complex multi-step problem in your own work, do not just ask it for the final answer. Apply Filip's methodology. Force the model to maintain a separate planning document. Make it explicitly state its assumptions, document its failures, and outline its logic before it executes the next step.
Don't let it wing it.
By externally forcing that executive function, you unlock a level of reasoning you simply won't get from a standard prompt.
It redefines what prompt engineering actually is. It's not about asking the right question, it's about building the right cognitive scaffolding for the machine.
Precisely.
But before we let you go, this paper raises an incredibly deep, almost unsettling question about the future of human knowledge.
It does. And this is something I want you to sit with today. In the case of these Hamiltonian cycles, Donald Knuth was able to step in, translate the AI's Python code into C, reverse engineer the logic, and write a traditional human-readable proof to verify that the 760 generalizations were true.
Right, he could check the work.
He could double-check the machine's math. This raises an important question. What happens a few years from now when an AI generates a solution to a problem in physics, biology, or mathematics that involves a level of multidimensional complexity so vast, or a chain of logic so utterly alien to our cognitive architecture that no human alive has the capacity to reverse engineer it?
Wow.
Will we reach an epistemological breaking point where we can no longer verify the truth, and we simply have to accept the discoveries of the machine on pure blind faith?
That is a staggering thought to leave on. When the math leaves the realm of human comprehension, how do we know what is actually true?
We might not.
It is exactly the kind of question that makes exploring the frontier of this technology so worthwhile. Thank you so much for joining us as we unpacked this incredible piece of source material. Keep questioning, keep exploring, and we will catch you on the next deep dive.